induction and Faraday's law. So before that, we discussed about electromotive force. We saw the relationship of any kind of electromotive force to the electric field. So we said EMF equals to the integral over a closed curve of the electric field close to DL. And we also saw that this is related to the change in magnetic flux, and say this is the same as minus of d phi by dt. And so Faraday's law is basically, it just tells you there is going to be an induced electromotive force if you change the magnetic flux. So delta V induced is minus d phi by dt. That's Faraday's law. And this induced voltage induces current, and the direction of this current is determined by what law? Lenz's law. So delta V induced gives you I induced, and that's determined by Lenz's law. So that's what we discussed last time. And so today we will see one of the fundamental equations in Maxwell's equations, which comes from Faraday's law. So far what we saw is the divergence of B equals to 0, the divergence of E equals to what? Rho over epsilon naught, and the curl of E is 0 so far in electrostatic, and the curl of B is equal to mu naught J. So after the next chapter, I believe this chapter and the next chapter, we just obtain all Maxwell's equations, which are the basis for electromagnetic field theory, optics, and whether it's quantum or classical optics, it all started from Maxwell's equation. So today, what we'll see is that the curl of the electric field is no more 0 if there is a changing magnetic field. So if EMF is related to an electric field, and if you have an induced voltage which results from change in magnetic flux, then you can imagine there is an induced electric field resulting from the change in magnetic flux. So if I write this, E induced, this is induced electric field. So the L is equals to minus of d phi by dt. Changing in magnetic flux produce a voltage produce a current. Current then is a motion of charges, so if the charges are moving, there has to be some kind of electrical force, which is the result of some electrical field, which we call induced electric field. So from Stokes' theorem, we can write this as, if you apply Stokes' theorem, this is the same as the curl of the electric field induced dotted dn. So this must be equal to minus of d phi by dt. So what this means is that if you have conductor, closed conductor, and you put this closed conductor in some magnetic field. So that's the magnetic field B. And if this magnetic field is changing, then the flux through this area is going to change. That generates an induced voltage, which generates an induced current. So you would start to see charges flowing in this conductor, and the flow of these charges is going to be some induced electric field. So if I express the flux phi in terms of the magnetic field, what's going to be? Phi is going to be the integral of the magnetic field dotted dA over this area. So, you know, induction of current can result by changing the strength of the magnetic field, and also by rotating this loop. So you can change the flux by changing the B field or the orientation of the closed loop. But for now, we will assume that the change in flux comes from the change in magnetic field. So for that, then I can write, assume the change in flux is due to change in B. But the area in change can also generate a change in magnetic flux. So if we assume that, then we would have the integral over the area of current of E induced dotted dA is going to be minus d by dt of the flux. So the flux, if you use this one for the flux, you would have integral of B dotted dA. So if we assume the change is only due to B, then you can write this as minus the integral of dB by dt dotted dA over the same area, and here you have over the same area current of the electric field induced dotted dA.
So on the right side, that's saying that just the area isn't changing?
Yeah, the area is not changing. Yeah. We assume just only flux resulting from changing magnetic field. So this then leads to the curl of the electric field induced equals to minus of dB by dt. So that is Faraday's law. This is Faraday's. So today what we will see is most of the application of this equation. We'll do several examples. So we will start with a simple example here. If you have a long cylindrical magnet of length L and a radius A, it carries a uniform magnetization M parallel to its axis. It passes with a constant velocity V through a circular wire ring of slightly larger radius B. So the first part of the question is plot a qualitative graph for the magnetic flux as a function of time. So you have this closed conducting loop, and you start to move